Look up at the night sky, and you might imagine a serene, orderly universe, stars twinkling peacefully, galaxies drifting calmly through the dark. But venture just 12 million light-years from Earth, and that tranquil picture shatters. Meet the Cigar Galaxy, officially known as Messier 82, a place where cosmic chaos reigns supreme. This isn't some quiet corner of the universe. It's a stellar factory operating at a frenzied, almost violent pace, birthing new stars 10 times faster than our own Milky Way. Supernovas explode like fireworks, colossal winds blast matter across space, and immense magnetic fields twist reality itself. This is a galaxy on fire, a celestial spectacle that defies everything we thought we knew about how galaxies live and die. And yet, the more we study it, the more mysteries we uncover. The Cigar Galaxy doesn't just break the rules, it rewrites them. From unexplained radio signals to ghostly gamma-ray emissions, from enigmatic black hole behavior to structures that shouldn't exist, this galaxy is a treasure chest of cosmic oddities. Each strange phenomenon pulls us deeper into a story of creation and destruction happening on an unimaginable scale. What keeps this galaxy burning so bright? What hidden forces are at play in its chaotic core? And what can its extreme nature teach us about the birth and death of stars everywhere? In this video, we're diving headfirst into the heart of the Cigar Galaxy to unpack 30 of its most bizarre and captivating phenomena. We'll explore stellar nurseries where stars are born in raging infernos, witness black holes that defy physics, and decode signals from the depths of space that leave even the brightest astronomers scratching their heads. This isn't just a tour of strange sights, it's a journey to the edge of what we understand about the universe itself. So buckle up, we're about to venture into one of the most explosive, mysterious, and spectacular regions of space ever discovered. But what drives such a spectacular, fiery display? The answer begins with a cosmic engine of unimaginable power, a supergalactic wind. This isn't a gentle breeze, it's a hurricane of cosmic proportions, roaring out from the galaxy's heart at speeds reaching millions of miles per hour. This colossal outflow is essentially the galaxy's own breath, a direct result of its breakneck pace of star formation and death. To understand its sheer power, picture our own Milky Way as a calm, suburban neighborhood. In contrast, the Cigar Galaxy is like a non-stop rock concert in the middle of a fireworks factory. It's loud, chaotic, and constantly exploding with energy. Deep within its stellar nurseries, countless massive stars are being born. These aren't like our sun. They're behemoths that live fast and die young, exploding as supernovas within just a few million years. Each of these titanic detonations acts like a piston in a massive engine, collectively driving a vast wave of superheated gas and dust outward. This relentless barrage of explosions doesn't just push material around, it forges a unified, supersonic wind that blasts through the galaxy, sweeping up everything in its path. This wind is so immense that it doesn't just stop at the galaxy's edge. It carries the very building blocks of stars' hydrogen gas and heavy elements far out into the desolate void of intergalactic space, effectively seeding the cosmos with the raw ingredients for future generations of stars and planets. This phenomenal wind is also the master sculptor behind the galaxy's iconic shape. As it erupts perpendicularly from the central starburst disk, it elongates the surrounding clouds of gas and dust, pulling and stretching them into that familiar, slender cigar form we see from Earth. The reddish filaments visible in detailed images are actually giant streamers of ionized hydrogen gas, glowing like embers as they're violently blown out into space. So, when we admire the Cigar Galaxy's distinctive silhouette, we are not just looking at a static shape, we are witnessing a snapshot of a dynamic, violent, and ongoing process of creation and dispersal, a testament to the incredible force that star birth can unleash. Now, to truly grasp the scale of this galactic wind, we must peer directly into the furnace that fuels it, the galaxy's chaotic and brilliant starburst core. This isn't just a cluster of stars, it's a cosmic metropolis in the midst of a historic construction boom, a region so dense and so prolific that it defies all earthly comparisons. Nestled within the central 1,000 light-years of M82, this core is a roiling cauldron of creation, where stars are being forged at a rate that is almost unimaginable. While our entire Milky Way galaxy might give birth to roughly one new star per year on average, the core of the Cigar Galaxy is producing them at a staggering rate 10 times faster, lighting up the darkness with the fire of 100 million suns. The secret to this incredible productivity is an immense reservoir of raw material. Vast, dense clouds of molecular gas and dust, the very building blocks of stars, have been funneled into the galaxy's center, likely due to gravitational interactions with its massive neighbor, the spiral galaxy M81. This event effectively crammed an entire galaxy's worth of star-forming fuel into a relatively tiny central region, creating the conditions for a perfect storm of starbirth. Within these cold, dark clouds, pockets of gas collapse under their own gravity, heating up until nuclear fusion ignites in their cores and new stars blaze to life. But unlike the relatively solitary birth of a star like our Sun, this process is happening on an industrial scale, with countless stars being born simultaneously in a packed, frantic environment. This extreme density has profound consequences. The newborn stars here are not just numerous, they are overwhelmingly massive, blue-hot giants that burn brilliantly and die quickly. Their intense ultraviolet radiation floods the surrounding gas clouds, causing them to glow with a fierce, hot light and carving out vast cavities. The region is so crowded and so luminous that if you were to stand on a hypothetical planet near this core, the night sky would be perpetually lit up, not by a few familiar constellations, but by a continuous, blinding daylight from the countless nearby stars, with new ones appearing like constant flashes in the sky. This incredible firepower is why the Cigar Galaxy's heart shines so brightly in infrared light. The visible light emitted by these new stars is almost entirely absorbed by the thick, surrounding cocoons of dust they were born from. This dust doesn't destroy the light, it soaks it up, heats up, and then re-radiates the energy at longer, infrared wavelengths. To our infrared telescopes, this core doesn't just look bright, it absolutely blazes, outshining the entire rest of the galaxy and revealing the true, hidden intensity of the starburst within. It's a dazzling, invisible inferno, a testament to the raw power of cosmic creation happening on a scale we rarely see elsewhere in the universe. Yet, even the raw power of these stellar factories pales in comparison to the enigmas lurking just outside the core. Scattered throughout the Cigar Galaxy are objects so bizarre and energetic that they defy simple classification: ultra-luminous X-ray sources, or ULCs. Imagine a single object in space, no larger than a city, that outshines a million suns. But this isn't ordinary light. It's a blistering torrent of high-energy X-rays, and M82 is absolutely teeming with them, hosting some of the brightest and most puzzling ULXs ever discovered. The mystery of these objects lies in a fundamental rule of physics known as the Eddington limit. It's a cosmic speed limit for brightness, dictating that there's only so much radiation an object of a given mass can emit before that radiation becomes so powerful it literally blows the object apart. Think of it like trying to blast a rocket off a planet. If the thrust is too great, it just tears the vehicle to pieces instead of lifting it. For a ULX to break this limit so spectacularly, conventional stellar mass black holes, which are typically up to 20 times the mass of our Sun, simply shouldn't be capable of it. Their gravitational grip isn't strong enough to hold onto the matter they're devouring while it shines with such ferocious intensity. This has led astronomers to a thrilling possibility. Perhaps some of these ULXs are not mere stellar remnants, but something far more exotic and elusive: intermediate mass black holes. These would be the cosmic missing link, weighing in at hundreds or even thousands of solar masses. bridging the gap between the small black holes formed from dying stars and the supermassive giants that anchor galactic centers. An object of that immense mass would have a gravitational pull powerful enough to overcome the Eddington limit, allowing it to gorge on surrounding gas and dust and shine with the incredible X-ray luminosity we observe. Finding one would be a monumental discovery, rewriting our understanding of how black holes form and grow. However, the plot thickens further. Not all ULXs may be solo acts. Another compelling theory suggests they could be unusual binary star systems where a normal black hole or neutron star is feeding from a companion star at an abnormally high and unsustainable rate. In this scenario, the incredible outpouring of energy might not be a violation of physics, but rather a brilliant optical illusion, a focused beam of X-rays, much like a cosmic lighthouse that is pointed directly at us. If we're looking straight down the barrel of this beam, its intensity would appear vastly brighter than if we were viewing it from the side, potentially creating the illusion of a far more powerful object than it truly is. So the hunt is on within the chaotic clouds of M82 to determine the true nature of these brilliant beacons. Each flicker and flare in their X-ray output is a vital clue, a piece of data that could tip the scales toward one theory or another. They are more than just points of light. They are profound puzzles that challenge our very definitions of what is possible under the laws of physics, hidden within a galaxy that seems to specialize in the extraordinary. But the galaxy's energetic outbursts are not confined to its visible boundaries. If we shift our view from the fiery optical light to the quieter, more subtle radio waves, an even more staggering structure comes into focus. Extending far beyond the familiar cigar shape are two colossal, ghostly lobes, like immense hot air balloons made of pure energy, billowing out into the intergalactic void. These are radio jets and lobes, and they are a direct, permanent testament to the unimaginable violence happening deep within the galaxy's heart. These structures begin their journey at the central supermassive black hole or within the intensely active starburst region itself. Here, powerful magnetic fields and explosive events act like natural particle accelerators, far more powerful than anything we could ever build on Earth. They fling electrons and other charged particles outward at velocities approaching the speed of light, focusing them into two narrow, opposing beams known as jets. These jets, composed of this frenzied, magnetized plasma, act like cosmic fire hoses, shooting a focused stream of high-energy material hundreds of thousands of light-years into space. The journey doesn't end there. As these jets plow into the thin gas that exists between galaxies, they inevitably slow down and spread out. The particles, no longer confined to a tight beam, balloon outward, creating the massive, diffuse lobes we detect with radio telescopes. Within these vast regions, the electrons are forced to spiral along magnetic field lines, and this motion causes them to emit synchrotron radiation, the very radio waves that allow us to see them. This process effectively traps the energy of the original explosion, storing it in these enormous, invisible structures for millions of years. The sheer size of these lobes is what truly underscores the Cigar Galaxy's power. They are not a minor feature. They dwarf the visible galaxy itself, serving as a permanent cosmic fossil record of past outbursts. Each lobe is a reservoir of ancient energy, a reminder that the galaxy's violent activity is not a momentary flare-up but a fundamental, enduring aspect of its character. By studying their shape and size, astronomers can essentially read the history of the galaxy's most energetic phases, understanding the power and duration of eruptions that occurred long before humans ever looked up at the stars. This incredible wind we've been discussing does more than just shape the galaxy. It's actively dismantling it from the inside out. One of the most staggering discoveries within M82 is the colossal outflow of molecular gas, the very lifeblood of star formation. We're not talking about the hot, ionized gas of the superwind. This is something far colder, denser, and more substantial. Imagine entire giant molecular clouds, the same colossal nurseries where stars are born, being physically ripped from the galaxy's core and hurled into the void. This isn't a gentle leak, it's a hemorrhage on a galactic scale, a cosmic exodus of truly epic proportions. The sheer volume of material involved is almost impossible to comprehend. Observations have revealed that this outflow contains enough molecular hydrogen and other heavy elements to form tens of millions of stars like our Sun. This is not mere trace amounts of gas. It's a significant fraction of the galaxy's entire future potential, its next generation of stellar inhabitants being permanently lost. This material is being ejected at breathtaking speeds, traveling fast enough to completely escape the galaxy's gravitational pull. Once it enters the desolate realm of intergalactic space, it is highly unlikely to ever return, forever diluted into the near-perfect vacuum that separates galaxies. The mechanism behind this incredible expulsion is a perfect example of cosmic feedback. The relentless barrage of supernova explosions and the intense radiation from countless massive stars in the starburst core don't just create a wind, they inject enormous energy into the surrounding environment. This energy doesn't only push the hot gas, it sweeps up the colder, denser molecular material that would normally collapse to form new stars. It's a cosmic tug of war where the very engines of creation are so powerful that they end up destroying the fuel source for future creation. The galaxy is essentially eating its own seed corn, burning through its resources at an unsustainable rate in a furious burst of productivity. This process has profound implications for the ultimate fate of the Cigar Galaxy. By violently expelling its remaining star-forming gas, the galaxy is effectively ensuring that its current starburst phase will be both brilliant and brief. It is a celestial spectacle that cannot last. In perhaps 100 million years, a mere blink in cosmic time, the frenzy of star birth will cease. The remaining massive stars will burn out and explode, and with no new gas to form replacements, the galaxy will gradually dim and quiet down. This massive outflow is therefore a key piece of the puzzle, explaining why galaxies like M82 represent a dramatic but short-lived phase of galactic evolution. We are witnessing a galaxy in its glory days, shining with incredible intensity precisely because it is spending its entire future all at once. Yet for all its visible fury, if you could only see the Cigar Galaxy with your own eyes, you'd be missing most of the show. The true, staggering intensity of its starburst heart is hidden, blazing in a part of the spectrum invisible to us, the infrared. This is the phenomenon of infrared hyperluminosity, and M82 is one of its most extreme examples in the entire universe, shining hundreds of times brighter in infrared light than it does in the visible light our eyes can see. To understand why, we need to step inside the chaotic core. Remember those countless massive blue hot stars being born at a frantic pace. They are pouring out a torrent of ultraviolet radiation, the most energetic kind of light. But between these stars and the cold void of space lies a formidable obstacle, a thick, choking shroud of cosmic dust. This isn't the dust you find on a shelf. It's a fog of microscopic particles, the heavy element soot left behind by generations of supernova explosions. This dust cloud acts like a massive, light-absorbing blanket wrapped around the entire stellar nursery. When the powerful ultraviolet light from the new stars slams into these dust grains, it doesn't just bounce off. The dust absorbs that energy, much like a black asphalt parking lot soaks up the heat of the sun on a summer day. This energy excites the dust, heating it up to temperatures ranging from tens to hundreds of degrees. And according to the fundamental laws of physics, any object that is heated glows, but it does so at a wavelength that corresponds to its temperature. Because the dust is relatively cool compared to the surface of a star, it doesn't re-emit the energy as visible light. Instead, it releases it as long-wave infrared radiation, what we essentially feel as heat. This process effectively transforms the entire central region of the galaxy into a colossal infrared light bulb. The furious energy of Starburst is being absorbed, converted, and then re-radiated on a truly monumental scale. This is why infrared telescopes like Spitzer and Herschel reveal the Cigar Galaxy not as a slender shape, but as an overwhelming, brilliant beacon of heat that absolutely dominates its region of space. The visible galaxy we admire in photographs is merely the tip of the iceberg. The brilliant infrared glow is the immense hidden bulk of its awesome power. This hyperluminosity makes M82 a critical laboratory for understanding the most intense episodes of star formation in the cosmos. By measuring its infrared output, astronomers can effectively peer behind the dusty curtain to calculate the true, staggering rate of star birth happening within, a rate that would otherwise be completely obscured and impossible to gauge. It stands as a brilliant testament to the fact that the universe's most dramatic events are often playing out in wavelengths beyond our natural perception, waiting for our technology to reveal their full, spectacular story. If you thought the Cigar Galaxy star-forming frenzy was impressive, consider the inevitable, spectacular conclusion to all that birth, death on an industrial scale. This galaxy doesn't just create massive stars, it obliterates them at a rate that is almost unheard of, earning it a well-deserved reputation as a supernova factory. While astronomers might expect a supernova event in a typical galaxy like our Milky Way to occur roughly once or twice a century, M82 is on a completely different schedule. In just the last few decades alone, we have witnessed multiple supernovas detonating within its confines, a statistic that speaks volumes about the frantic, high-stakes environment within its chaotic core. This relentless barrage of stellar explosions is the direct and inevitable consequence of its breakneck pace of star birth. The Starburst core is a production line for massive, blue supergiant stars, the kind that live fast and die young. Unlike our stable sun, which will burn for billions of years, these stellar titans exhaust their nuclear fuel in a cosmic blink, lasting only 10 to 20 million years. Their immense mass creates enormous pressure in their cores, accelerating fusion and leading to a swift and violent end. In the densely packed core of M82, where countless such stars are born simultaneously, their deaths are also synchronized, creating a near-constant fireworks display of catastrophic finales. Each one of these explosions is a universe-altering event in its own right. A single supernova can, for a brief period, outshine its entire host galaxy. But in M82, the effect is cumulative and transformative. These aren't just isolated flashes of light, they are the primary engine driving the galaxy's most dramatic features. The collective force of these repeated blasts is what powers the colossal supergalactic wind, pumping energy and enriched material into the surrounding space. It's this relentless churning of stellar death that continuously heats the surrounding gas, accelerates particles to incredible speeds, and forges the heavy elements essential for forming planets and ultimately life itself. The most recent and visually striking example occurred in 2014 with the discovery of supernova 21-4J, a Type Ia supernova. This particular kind of explosion is famously used as a standard candle for measuring cosmic distances because of its predictable brightness. To find one blazing so brightly within the already luminous Cigar Galaxy provided astronomers with a rare and precious opportunity. It allowed them to calibrate their measurements of this turbulent galaxy with incredible precision, effectively using the violent death of a star as a celestial yardstick to better understand the very galaxy that spawned it. This high rate of stellar demise presents a unique opportunity for scientists. Most astronomical events are once-in-a-lifetime occurrences, but in M82, supernovas are a recurring feature. This allows astronomers to study different types of supernovas, their light curves, and their remnants in various stages of evolution, all within the same galactic laboratory. They can observe how a fresh shockwave expands and interacts with the complex pre-existing structure of the superwind, or how the ejected material from one explosion is swept up by the next. This turns the galaxy into a living classroom, offering a continuous stream of data on the life cycle of stars and their profound impact on the evolution of their galactic home. Yet for all the visible chaos of winds and explosions, one of the most profound and invisible forces shaping the Cigar Galaxy is its magnetic field. This isn't a simple, orderly magnetic field like the one surrounding a bar magnet. It's a cosmic tapestry of organized chaos, a complex web of magnetic force lines that weave through the entire galaxy, influencing everything from the flow of gas to the very birth of stars in ways we are only beginning to comprehend. To grasp why this is so unusual, picture a typical spiral galaxy. Often, its magnetic field will follow a relatively calm, large-scale pattern, elegantly tracing the graceful spiral arms. But in M82, that order is shattered. The field is turbulent and incredibly strong, amplified by the non-stop violence of the Starburst core. The relentless churn of supernova explosions acts like a colossal dynamo, constantly stirring and stretching the magnetic field lines, tangling them into a state of intense, frenetic energy. This isn't a passive background force, it's an active, dynamic player in the galaxy's drama. One of the most startling discoveries is how this magnetic field interacts with the iconic superwind. Instead of being blown into a random, messy cloud, the dust and gas being ejected from the galaxy's core are actually channeled and shaped by these powerful magnetic forces. Observations reveal that the field is aligned perpendicular to the galactic disk, running parallel to the direction of the wind itself. It acts as a kind of cosmic guide rail, helping to focus and collimate the outflow, which is part of the reason the wind can maintain its incredible structure over such vast distances. The very filaments of hot gas that create the galaxy's smoky appearance are likely held together and organized by this invisible magnetic scaffolding. The influence of this field extends right down to the process of star formation itself, creating a fascinating paradox. On one hand, magnetic fields can provide support against gravity within a gas cloud, preventing collapse and potentially putting a brake on star birth. But in the extreme environment of M82, the field is so tremendously amplified that it may actually be doing the opposite. By adding extra pressure and turbulence to the already dense molecular clouds, it could be triggering a faster and more efficient collapse, essentially compressing the gas and igniting the formation of even more massive stars. It's a delicate and poorly understood balance, a magnetic field that might be both a moderator and an accelerant for the galaxy's furious pace of creation. Unraveling this mystery requires looking at the galaxy in a completely different light, specifically polarized light. As dust grains in space are spun and aligned by magnetic fields, they emit light that is polarized, meaning its waves vibrate in a preferred direction. By meticulously mapping this polarized emission, astronomers can indirectly trace the invisible magnetic field lines, creating a map of the forces at work. The resulting images are both beautiful and bewildering, showing a field that is both large-scale in its overall direction, yet incredibly tangled and complex in its fine details, a perfect reflection of the galaxy itself. A place where immense power and intricate structure exist in a state of controlled chaos. But what set this entire cosmic spectacle in motion? To find the true origin of the Cigar Galaxy's fury, we must look beyond its borders to a dramatic, gravitational dance with its colossal neighbor, the majestic spiral galaxy Messier 81. Millions of years ago, these two galactic giants had a close encounter, a celestial event that was far from a gentle meeting. It was a gravitational assault that forever altered the destiny of M82, wrenching it from a likely quiet existence and triggering the violent starburst that defines it today. This tidal interaction is the master key that unlocked the galaxy's potential for chaos. Imagine the immense, invisible force of gravity as a cosmic sculptor. As M82 swung past the much larger M81, the difference in gravitational pull across the smaller galaxy was enormous. The side closer to M81 was tugged much more strongly than the side farther away. This effect, known as a tidal force, acts less like a pull and more like a stretch, relentlessly warping and distorting the very shape of the galaxy. It's the same force our moon exerts on Earth's oceans to create tides, but here, operating on a scale of hundreds of thousands of light years, the consequences were infinitely more profound. This gravitational stretching did something critical. It disrupted the orderly flow of material within M82. Vast reservoirs of neutral hydrogen gas that were once peacefully orbiting the galactic center were thrown into disarray. Their trajectories were violently altered, and instead of stable circular paths, they were sent plunging inward toward the galaxy's core. This event funneled an unimaginable amount of star-forming fuel, enough gas to form billions of stars, into a relatively tiny central region no more than 1,000 light-years across. It was as if a celestial hand had forcefully squeezed a giant, diffuse cloud of gas into a tight, incredibly dense ball. Within this suddenly overstuffed core, the conditions became perfect for a chain reaction of starbirth. The fundamental rule of star formation is that dense gas clouds collapse under their own gravity. By cramming so much material into such a small space, the tidal forces from M81 dramatically increased the density and pressure, pushing countless gas clouds over the critical threshold for collapse. The shock waves from the interaction itself likely traveled through the gas, creating ripples of compression that further catalyzed the process. This was the spark that lit the fuse, igniting the frantic burst of star formation that has been raging ever since. This story transforms our understanding of the Cigar Galaxy from a solitary wonder into a character in a larger cosmic drama. Its spectacular fire is not merely a random occurrence, it is a direct consequence of its relationship with its environment. The encounter with M81 provided the initial trigger, but the aftermath has a life of its own. The starburst it ignited now fuels the superwind, which in turn is expelling gas and shaping the galaxy's future. This tidal interaction is the prime example of how galaxies are not isolated islands in space but social entities whose collisions and close encounters are fundamental drivers of their evolution, capable of turning tranquility into a firestorm of creation. And just when we thought we had a handle on the forces shaping this galaxy, a far more fundamental and perplexing mystery emerges from the shadows, one that challenges our understanding of the universe's very fabric. For decades, the prevailing model of cosmology has rested on a cornerstone concept, dark matter. This invisible, mysterious substance is believed to form a massive halo around every galaxy, a gravitational scaffold that holds the bright, visible stars and gas together. Without the immense extra pull of dark matter, the rapid rotation of a galaxy's outer regions would simply fling stars into the void. Yet, when astronomers began to carefully measure the mass of the Cigar Galaxy, they encountered something startling. The numbers didn't add up. Observations of the motions of stars and gas within M82 suggest it may possess significantly less dark matter than any standard model would predict for a galaxy of its size and type. This isn't a minor accounting error, it's a potential crisis for our cosmic models. The primary method for estimating a galaxy's dark matter content is to measure its total mass through the gravitational influence it exerts, essentially watching how stars and gas move, and then subtract the mass we can actually see from stars, gas, and dust. The leftover, hidden mass is the dark matter. In a typical galaxy, this dark component dominates, making up over 80% of the total mass. But in M82, that missing mass seems to be, well, even more missing than expected. The gravitational pull needed to explain the motions of its outer material appears weaker, implying a much less massive dark matter halo than anyone anticipated. So, where did it go? One compelling theory directly connects back to the galaxy's extreme nature. Think about the phenomenal superwind, that hurricane of material being blasted out from the core. This wind isn't just composed of ordinary matter. It's a complex soup of hot gas, cosmic rays, and magnetic fields, all expanding with incredible force. Some astrophysicists propose that this relentless outflow could be physically pushing against and disturbing the halo of dark matter itself. While dark matter doesn't interact with light or normal matter in any way other than through gravity, a sufficiently powerful and sustained event could potentially gravitationally sweep or distort the dark matter distribution, effectively thinning it out in the central regions or even ejecting some of it entirely from the galaxy. Another fascinating possibility is that we're not seeing a lack of dark matter, but rather a misinterpretation of the evidence. The Cigar Galaxy is not a calm, serene, and stable system where simple orbital mechanics apply. It is a galaxy in the throes of a massive, violent outflow. The motions of gas and stars that we measure are not purely gravitational. They are also driven by the tremendous pressure of the superwind and the constant bombardment of supernova shocks. This means the velocity we observe isn't just a clean indicator of the gravitational mass, it's a messy combination of gravity and intense hydrodynamical forces. We might be underestimating the true dark matter content because other, more violent energies are dominating the motion we see. This enigma pushes our observational capabilities to their limit. Pinpointing the dark matter distribution requires incredibly precise measurements across the entire galaxy, a task complicated by its edge on orientation and the chaotic fog of its starburst core. Each new observation adds a piece to the puzzle, but the full picture remains elusive. The case of the missing dark matter in M82 forces us to ask profound questions. Are we witnessing a unique event where normal matter has temporarily overwhelmed its dark counterpart? Or does this intense starburst phase represent a fundamental way that galaxies can alter their own dark matter halos, a process we never before imagined was possible? The answer could reshape not just our view of this single galaxy, but of dark matter itself. Deep within the turbulent heart of the Cigar Galaxy, another incredible engine is at work, one that operates on a scale that makes our most powerful machines on Earth seem like children's toys. Beyond the blazing starburst and the roaring superwind, M82 is functioning as a natural particle accelerator of almost unimaginable power, generating a storm of high-energy cosmic rays that flood out into the vastness of intergalactic space. These aren't rays of light, they are subatomic bullets, primarily protons and atomic nuclei hurtling through the vacuum at velocities perilously close to the speed of light, each one carrying a tremendous amount of energy. The secret to this phenomenal acceleration lies in the galaxy's relentless chaos. The core is a maelstrom of supernova explosions, with massive stars dying in violent blasts every few years. Each supernova doesn't just light up the cosmos, it sends a powerful shockwave rippling outward through the surrounding clouds of gas and magnetic fields. These expanding shock fronts act like enormous, natural versions of the particle accelerators we build on Earth, such as the Large Hadron Collider. As a charged particle, a proton, for example, encounters this moving wall of energized gas, it can become trapped, bouncing back and forth across the shockwave like a rubber ball in a rapidly closing hallway. With each crossing, the magnetic fields embedded in the shock front give the particle another kick, another boost of energy, accelerating it to ever higher speeds. This process, known as diffusive shock acceleration, can continue until the particle is finally ejected from the turbulent region, flung out into the galaxy and beyond with enough energy to cross the immense voids between galaxies. The sheer number of supernovas in M82 means this process is happening constantly, on an industrial scale, turning the galactic core into a factory that mass produces these ultra-fast, high-energy particles. For decades, astronomers have been trying to pinpoint the exact origins of the cosmic rays that constantly bombard our own planet's atmosphere. While lower energy rays come from our Sun, the source of the most energetic ones has been a long-standing mystery. The Cigar Galaxy presents a compelling candidate. Its intense starburst activity and the resulting superwind create the perfect conditions for generating a huge flux of these particles. What's more, the superwind itself provides a clear, focused pathway for them to escape, funneling them out of the galaxy and into intergalactic space where they can travel for millions of years. The evidence for this is building. Scientists using sophisticated observatories like the Veritas Gamma-Ray Telescope Array have detected very high-energy gamma rays emanating from M82. Gamma rays are the telltale sign of cosmic ray activity. They are produced when these accelerated protons collide with the nuclei of atoms in the dense gas clouds of the galaxy. The resulting collision creates a shower of secondary particles, including pions, which then decay into gamma rays. By detecting this specific gamma ray signature, we are essentially seeing the glowing aftermath of the cosmic ray production process, confirming that the galaxy is indeed a powerful source. This has profound implications that stretch far beyond the Cigar Galaxy itself. The cosmic rays it generates become part of the background sea of radiation that permeates the entire universe, influencing the evolution of other galaxies and even the formation of stars within them. These high-energy particles can penetrate giant gas clouds, injecting energy and heat, which can either promote or stifle star formation by preventing gravitational collapse. In a very real sense, the violent processes happening in one dwarf galaxy 12 million light-years away are contributing to the cosmic ecosystem, their effects rippling across the cosmos and subtly influencing the story of creation everywhere. This brings us to a more subtle, yet equally fascinating mystery hidden within the smoky plumes of the superwind, the very dust itself. When we gaze at the beautiful reddish filament stretching out from the Cigar Galaxy, we're looking at countless trillions of microscopic dust grains, the cosmic soot that gives the galaxy its distinctive, smoky appearance. But this isn't your average, everyday galactic dust. When astronomers analyzed its composition using infrared spectroscopy, they found something startlingly unusual. The chemical makeup of these grains defies the standard recipes we see almost everywhere else in the universe, presenting a clear and puzzling anomaly. In a typical, quieter galaxy like our Milky Way, interstellar dust follows a fairly predictable formula. It's primarily composed of silicates, think tiny particles similar to sand or glass, mixed with various carbon-based compounds, often coated in a mantle of frozen water ice and other simple ices. The ratios of these materials are generally consistent, a testament to the relatively steady, though still violent, cycle of star birth and death. But the environment within M82 is anything but steady. It's a supernova factory, and this constant barrage of stellar explosions appears to be cooking up a completely different kind of dust with a bizarre chemical signature. The key to this strange composition lies in the unique conditions within the supernova shocks themselves. A typical supernova explosion creates an immensely powerful shock wave that slams into the surrounding gas and dust. This shock does two contradictory things. It can destroy pre-existing dust grains, vaporizing them back into their constituent gas atoms, but it can also provide the immense pressure and heat needed to forge entirely new types of grains from the resulting soup of elements. In most galaxies, this process happens occasionally, allowing for a balance, but in M82, the shockwaves are continuous and overlapping, creating a sustained, extreme environment unlike any other. This relentless processing seems to favor the creation of certain resilient compounds over others. For instance, observations suggest an overabundance of certain types of carbon-rich dust, like graphite or even more exotic forms of carbon molecules, while the expected silicate grains appear relatively underabundant. One theory is that the ferocious radiation and shock temperatures in the starburst region are simply too high for more fragile silicate structures to form or survive. Carbon grains, particularly those that form in a graphitic structure, are incredibly tough and can withstand these hellish conditions much more effectively, allowing them to persist and accumulate. Furthermore, the sheer volume of heavy elements being forged in the supernova provides an unprecedented supply of raw ingredients. Each dying massive star is a crucible of nucleosynthesis, creating vast amounts of elements like carbon, oxygen, silicon, and iron, and spewing them out into the chaos. The dust-forming regions are therefore flooded with these newly minted atoms, allowing for chemical reactions and condensation sequences that are simply too rare or inefficient to occur on a significant scale in a galactic environment. It's like comparing a home kitchen to a massive industrial chemical plant. The scale and intensity of the processes produce a different end product altogether. This dust composition anomaly is far more than a trivial curiosity. It has profound implications for the entire ecosystem of the galaxy. Dust grains play a critical role in cooling gas clouds, shielding forming stars from harsh radiation, and even serving as the building blocks for planets. If the dust in M82 has fundamentally different properties, how it absorbs heat, how it catalyzes chemical reactions, how it clumps together, then the very process of star and planet formation there could be unlike anything we see elsewhere. The galaxy's extreme nature may be writing its own rulebook on cosmic chemistry, one supernova explosion at a time. This same particle accelerator engine that churns out a steady stream of cosmic rays is also capable of sudden, dramatic, and mysterious outbursts. If we train our most sensitive gamma-ray telescopes on the Cigar Galaxy, we witness a source that refuses to behave predictably. Its high-energy gamma-ray emission is anything but constant. It flickers, flares, and at times brightens dramatically for reasons that continue to baffle astronomers. This isn't a gentle fluctuation, it's a signal that the most violent processes within the galaxy can turn on and off, or ramp up to incredible intensities in ways our current models struggle to explain. Gamma rays represent the most energetic form of light in the universe, and their production is always tied to the most extreme events. In M82, the prevailing theory points back to those accelerated cosmic rays. When a high-energy proton, accelerated by a supernova shock, smashes into a slower-moving proton within a dense cloud of gas, the collision can create a short-lived particle called a neutral pion, which almost immediately decays into two gamma-ray photons. This process should, in theory, produce a relatively steady glow, its intensity tied directly to the density of the gas and the number of cosmic rays. A major flaring event, therefore, implies a sudden, colossal surge in one of these two ingredients. So what could cause such a dramatic surge? One compelling idea revolves around the source of the cosmic rays themselves. Perhaps a particularly titanic supernova exploded in an exceptionally dense region of gas. The initial shockwave from such an event would not only accelerate a massive new wave of particles, but also violently compress the surrounding gas, dramatically increasing the target density for collisions. The result would be a brilliant, temporary flash of gamma rays, a cosmic flashbulb that fades as the shockwave expands and weakens. In a galaxy producing so many supernovas, catching one at just the right moment could explain a flare. But the timing and scale of some observed flares push against this simpler explanation. The changes in brightness can be surprisingly rapid, happening over timescales of weeks or months. This presents a serious challenge because the region where the cosmic rays are accelerated, the entire central starburst zone, is hundreds of light years across. For the entire region to turn up, its output in unison so quickly would require a coordinated event of unbelievable synchronicity, like every cannon in a vast army firing at exactly the same instant without any command. This has led scientists to consider more exotic and focused culprits. Could the flaring be coming not from the diffuse starburst region, but from a single point-like source within it, such as one of those enigmatic ultra-luminous X-ray sources we discussed earlier? If a ULX, perhaps an intermediate mass black hole on a feeding frenzy, experienced a sudden, massive influx of material, the resulting accretion disk could generate intense jets and outbursts that produce their own localized storm of gamma rays. The shorter variability timescale would be much easier to explain if the eruption was confined to a single, powerful engine rather than the entire galactic core. Another fascinating, though more speculative, possibility involves the galaxy's immense magnetic fields. These fields are not just conduits for acceleration, they can also trap particles. Imagine a vast magnetic bottle holding a huge reservoir of accelerated protons. If something suddenly destabilized this bottle, a shockwave from a nearby supernova or a reconnection event in the tangled magnetic field, it could rupture, releasing all of its stored energetic particles at once into the surrounding dense gas. This would create a spectacular, short-lived gamma-ray flare as the pent-up cosmic rays violently collided with their targets. Each flicker from the Cigar Galaxy is therefore a coded message about the engines powering it. By meticulously monitoring these changes in brightness across different energy levels, astronomers are working to crack that code. The variability itself is a crucial clue, telling us about the size of the accelerator, the density of the environment, and the underlying physical mechanisms at work. In a galaxy that specializes in extremes, these gamma-ray flares represent the most volatile and unpredictable outbursts of all, reminding us that even within a constant state of chaos, there are still levels of intensity we have yet to fully understand. Tucked away within the turbulent starburst core of the Cigar Galaxy lies another of its profound mysteries, not a single explosive event, but a collection of incredible structures that represent a new chapter in stellar evolution. These are superstar clusters, and M82 hosts them in staggering numbers. To call them simply star clusters is a dramatic understatement. These are celestial citadels, colossal cities of stars that dwarf any similar grouping found in our own Milky Way. While a typical open cluster in our galaxy might contain a few hundred stars, and even a massive globular cluster holds a few 100,000, a superstar cluster packs millions of stars into a region only a few dozen light-years across, and density of stellar population that is almost incomprehensible. The environment required to forge such immense structures is as extreme as the clusters themselves. It all goes back to the enormous tidal forces from the encounter with M81, which funneled a galaxy's worth of gas into the tiny central region. This created molecular clouds of unparalleled density and mass. Within these cosmic pressure cookers, star formation didn't just happen, it occurred in a single, coordinated, and catastrophic collapse. Instead of forming individual stars scattered across a cloud, the entire cloud itself fragmented and condensed into a frenzy of simultaneous stellar birth, binding millions of new suns together by their immense mutual gravity in one glorious, violent burst. It's the difference between a quiet suburban neighborhood slowly building houses over decades and the instantaneous construction of a packed, towering megacity. What makes these superstar clusters so intriguing to astronomers is that they don't neatly fit into any existing category. They are not open clusters which are loose, young, and destined to eventually drift apart. And while they share the dense, spherical shape and immense star count of ancient globular clusters, they are not old. They are incredibly young, blazing with the hot blue light of massive newborn stars. This presents a fascinating possibility. We might be witnessing in real time the birth of objects that will one day evolve to resemble the ancient globular clusters that orbit modern galaxies. We are seeing the possible origin story for some of the universe's most ancient structures playing out in fast forward within this chaotic galaxy. Their youth and power have profound effects on their own survival. The sheer number of massive stars within a single superstar cluster means it is a constant source of tremendous energy. The fierce stellar winds and radiation pressure blowing from these hot giants act like a blowtorch, trying to violently disperse the very gas that gave them life. In a less massive cluster, this feedback would quickly shred the nursery, halting star formation and sending the young stars flying apart. But the gravitational grip of a superstar cluster is so powerful that it can withstand this internal rebellion. It holds its stellar population together against the incredible forces trying to tear it apart, allowing it to evolve as a single, coherent unit for billions of years. Studying these objects is like finding a living fossil in the process of being born. They offer a unique window into the conditions of the early universe, when intense starbursts and the formation of dense clusters were far more common. By analyzing their light, astronomers can determine their exact ages, compositions, and motions, piecing together the history of the starburst that created them. Each superstar cluster is a timestamp, a frozen moment that tells us about the incredible power and precision of the forces that shaped the Cigar Galaxy, revealing that even within its overwhelming chaos, there exists a level of order and structure on a truly monumental scale. But the story of these clouds doesn't end with their strange shapes. It extends to their very survival in such a hostile environment. The constant barrage of ultraviolet radiation from the massive stars is so intense that it doesn't just heat the clouds, it violently strips them apart in a process called photodissociation. Imagine a sandcastle being hit by a powerful wave. The structure is eroded and broken down into its constituent grains. Similarly, the energetic photons from the starburst blast into the clouds, breaking apart the fragile molecular bonds of the hydrogen gas and turning it back into a hot atomic state. This constant erosion creates a bizarre and dynamic life cycle for the clouds, where they are continuously being shattered by radiation and then potentially reformed by the very shock waves that their destruction helps to create. This extreme environment might also be forging a completely different kind of molecular cloud, one that is unique to galaxies like M82. Some astronomers theorize that the pervasive shock waves could be compressing the gas to such incredible densities that they form what are known as superdense clouds. These would be cores of molecular gas far denser and more pressurized than anything found in a common galaxy, providing the perfect high-pressure incubators for the formation of the superstar clusters we see. In this view, the chaos isn't just destroying the old structures, it's actively manufacturing new, more extreme ones, writing a new chapter on how interstellar matter can behave under the most severe conditions. Ultimately, these bizarre molecular structures are more than just curiosities. They are the key to understanding the future of the entire galaxy. The rate at which these clouds are being shattered and consumed dictates how long the current starburst can possibly last. They represent the remaining fuel for the cosmic fire, and the intense forces at play are ensuring that this fuel will be burned through at an astonishingly rapid pace. By studying their turbulent shapes and fragmented nature, we are essentially taking a direct measurement of the galaxy's metabolism, watching a celestial engine consume its own fuel with a frantic, unsustainable intensity that guarantees this brilliant chapter of its life will be both spectacularly bright and tragically short. As if the chaotic starburst and cosmic winds weren't enough, the Cigar Galaxy reveals yet another layer of mystery when we examine one of the most fundamental building blocks of the universe, neutral hydrogen gas. In a typical spiral galaxy, this cool, atomic hydrogen is predictably distributed in a vast, rotating disk, serving as the primary reservoir of fuel for future star formation. But M82 is no typical galaxy. When radio astronomers map the distribution and motion of this gas using instruments like the Very Large Array, they don't see a calm, orderly disk. Instead, they find a scene of utter pandemonium, a distribution so anomalous and fractured that it paints a picture of a galaxy that has been thoroughly shaken to its core. The most startling feature is the presence of vast, gaping voids where the hydrogen has been almost completely cleared out. These aren't just slight dips in density, they are enormous regions spanning thousands of light years that are strikingly devoid of the gas that should be there. It's as if a cosmic vacuum cleaner has swept through entire sectors of the galaxy, leaving behind nothing but an eerie emptiness. The cause of this clearing is no mystery. It's the direct and violent effect of the supergalactic wind. The relentless onslaught of supernova explosions has blasted the lighter, atomic hydrogen right out of the central regions, effectively scouring the galactic disk clean and creating these bizarre hollows in the interstellar medium. But the story doesn't end with absence. For all the gas that has been expelled, other pockets have been gathered up and thrown into chaotic motion. The observations reveal massive, fast-moving clouds of neutral hydrogen that are hurtling through the galaxy at velocities that completely defy simple gravitational expectations. These aren't just clouds drifting with the rotation of the galaxy. They are being shot like cannonballs, their motion dominated not by the serene pull of gravity, but by the explosive kinetics of the starburst-driven wind. Their trajectories are complex and tangled, some shooting out perpendicular to the disk, others streaming along bizarre, unexpected paths that indicate they are caught in the turbulent flows of the larger superwind. This presents a serious challenge for astronomers trying to measure the galaxy's total mass, including its elusive dark matter. The standard method for weighing a galaxy involves carefully measuring the rotation curve, how the orbital speed of gas and stars changes with distance from the center. In a calm, stable galaxy, this rotation is governed almost entirely by gravity, allowing us to calculate the mass pulling on it. But in M82, the motions of the hydrogen gas are a chaotic mess. The velocity you measure at any given point isn't a clean orbital speed. It's a jumbled combination of rotation, expansion, outflow, and turbulence. The force of the wind is so powerful that it has effectively overwhelmed the gentle tug of gravity in dictating how this gas moves, making it nearly impossible to use standard techniques to weigh the galaxy accurately. These high-velocity hydrogen clouds are more than just errant blobs. They are crucial cargo ships transporting heavy elements across the galaxy and beyond. As the superwind sweeps them up, they carry with them the enriched products of countless supernova elements like oxygen, carbon, and iron that were forged in the hearts of massive stars and scattered in their violent deaths. This process of mechanical feedback, where the galaxy's star formation activity directly alters the distribution of its own gas, is happening on a scale and with an intensity that is rarely observed elsewhere. The anomalous hydrogen distribution of M82 is therefore a stunningly clear snapshot of a galaxy in the midst of a profound transformation, its very lifeblood being violently redistributed by the very stars it created. Yet for all its brilliance across the spectrum, the Cigar Galaxy holds onto a counterintuitive secret, one that becomes apparent only when we look for it in the energetic glow of ultraviolet light. Given the sheer number of massive, hot, blue stars being born in its core, logic dictates that M82 should absolutely blaze in the UV, outshining almost every other galaxy in the local universe. These young stellar giants are ultraviolet powerhouses, and with so many of them, the combined output should be staggering. But when astronomers point their ultraviolet telescopes toward it, they are met not with a blinding beacon, but with a surprising dimness. This ultraviolet darkness is a profound paradox, a glaring absence of light where there should be an overwhelming presence, and it points to two fascinating and equally compelling explanations. The first and most straightforward culprit is the very thing that makes the galaxy's infrared glow so intense, its incredible abundance of dust. We must remember that ultraviolet light, while energetic, has a very short wavelength. This makes it particularly vulnerable to scattering and absorption by even the tiniest of interstellar dust grains. The starburst core of M82 isn't just dusty. it's shrouded in a thick, nearly impenetrable fog of cosmic soot, a byproduct of all those supernova explosions. The ultraviolet photons pouring out from the surfaces of hot young stars don't get far on their journey into space. Instead, they are almost immediately intercepted by this dense dust curtain. The energy from these photons is absorbed, heating the dust grains and causing them to re-radiate the energy at those longer, infrared wavelengths we detect so strongly. In this scenario, the galaxy isn't actually dim in ultraviolet energy. Its output is simply being converted or hidden behind a cosmological veil that transforms its light into a different form entirely. It's the astronomical equivalent of a brilliant spotlight shining directly into a thick bank of fog. The light is there, but an observer standing outside the fog sees only a diffuse, dull glow. However, some scientists suspect the answer might be more complex than just exceptional dust absorption. Could the stellar population itself be unusual? The incredible density and violence of the starburst environment might be altering the very way stars form and live. One intriguing theory suggests that the initial mass function, the rulebook that governs how many stars of each size are born in a cloud, might be skewed in M82. In a typical region like our own galactic neighborhood, for every single superstar of 100 solar masses, a cloud will form a multitude of smaller, sun-like stars. But in the extreme, pressurized environment of the Cigar Galaxy's core, the process of star formation might be biased, favoring the creation of an overabundance of these stellar behemoths. This might sound like it would produce even more UV light, but there's a catch. The most massive stars have the shortest lives. They might be burning out and exploding as supernovas so quickly that the galaxy's ultraviolet output is actually being snuffed out almost as fast as it is being created. The stellar population could be so top-heavy and short-lived that it never reaches a steady state of maximum UV brightness, leading to a lower overall than we would predict. Alternatively, the intense radiation pressure and powerful stellar winds within the densely packed clusters could be physically stripping the outer layers off these massive stars before they even have a chance to fully ignite and shine at their peak UV potential. Or the sheer crowding might lead to a high rate of stellar mergers, creating bizarre, short-lived objects that don't follow the standard life cycle. The ultraviolet darkness, therefore, might not be a simple case of something blocking the light, but rather a signature of a fundamentally different kind of stellar factory, one operating under rules we are only beginning to understand. This mystery forces us to look closer, to use the combined power of multi-wavelength observations to peer past the dust and census the stars themselves, searching for clues to what is truly happening inside this cosmic furnace. Tucked away amidst the fire and the fury, the Cigar Galaxy broadcasts its secrets on a far quieter frequency, using a natural amplifier of almost impossible precision. Scattered throughout its chaotic clouds are cosmic masers, natural microwave lasers that beam out intensely focused signals, acting as brilliant beacons that highlight some of the galaxy's most energetic and hidden processes. The term maser stands for microwave amplification by stimulated emission of radiation, and it operates on the exact same principle as a more familiar laser, but instead of visible light, it amplifies specific frequencies of microwave radiation. These aren't human-made instruments, they are entirely natural phenomena, and they occur in regions where conditions are just right. Imagine a cloud of gas rich in specific molecules like water or methanol. For a maser to fire up, this cloud needs to be pumped with energy, often from the intense radiation of a nearby young star or the shockwave from a supernova. This energy excites the molecules, boosting their electrons to higher energy levels. Then, when a passing microwave photon of exactly the right frequency triggers one of these excited molecules, it causes it to drop back down to a lower energy state, releasing an identical photon in the process. This starts a chain reaction, with the two photons then triggering the release of two more, and so on, creating a powerful, coherent beam of microwave light, all moving in the same direction like a perfectly synchronized chorus. In a common galaxy, masers are relatively faint and used by astronomers as precise tools to measure distances and motions. But in the extreme environment of M82, they become something else entirely. They are staggeringly luminous, orders of magnitude brighter than their counterparts in the Milky Way, and their signals flare and fade in unpredictable ways. This extreme behavior is a direct response to the galaxy's violence. The same shockwaves that accelerate cosmic rays and the intense radiation fields that photodissociate gas clouds are the powerful pumps energizing these molecular clouds to their breaking point, driving them to emit these brilliant, focused screams into the darkness. The specific molecules involved act as fingerprints, each telling a different part of the story. Hydroxyl masers reveal the workings of regions battered by shockwaves, while water masers often pinpoint the incredibly dense, hot gas swirling around newly forming massive stars or even the accretion disks of black holes. Methanol masers are particularly potent signposts, almost exclusively found in areas of intense, high-mass star formation, making them brilliant markers that guide astronomers directly to the galaxy's most active stellar nurseries, even when those nurseries are completely hidden behind thick veils of dust. By meticulously mapping the locations and strengths of these maser spots, scientists can create a detailed energy map of the galaxy's heart. Each bright point of microwave light is a probe, illuminating the physical conditions, the temperature, density, and turbulence within clouds that are otherwise completely opaque to our telescopes. They are nature's own diagnostic tools, allowing us to take the temperature of the cosmic furnace and understand the powerful forces that are shaping the galaxy from the inside out, revealing a layer of intricate structure within the overwhelming chaos. But perhaps the most profound chemical story is written not in the gas, but in the very stars themselves. Spectroscopic studies of individual supergiant stars within M82 reveal a fascinating and complex tapestry of elemental abundances. Some stars show the expected signature of rapid enrichment, high levels of oxygen, magnesium, and other alpha elements produced in core collapse supernova. Yet others, often in the same crowded region, display starkly different chemical fingerprints, with unusually high amounts of elements like yttrium, strontium, and barium. These so-called S-process elements are typically associated with the slower neutron capture processes in aging, lower-mass stars, which take billions of years to evolve. Their presence in a galaxy dominated by short-lived massive stars is a major puzzle, suggesting that the earliest generations of stars in M82 might have included a previously unknown population of rapidly evolving intermediate mass stars that could produce these elements on a much faster timescale. This strange chemical enrichment forces us to reconsider the entire life cycle of elements in an extreme environment. The galaxy appears to be operating its own distinct version of cosmic chemistry, one where the rules of element creation and distribution are being rewritten by the sheer intensity and frequency of its stellar explosions. The elements we see are not just the product of standard supernova models. They are the unique output of a system pushed to its physical limits, where the very processes of nucleosynthesis are amplified, altered, and perhaps even entirely new pathways are unlocked. By decoding these unusual abundance patterns, we are not just studying the Cigar Galaxy. We are glimpsing a more violent, efficient, and potentially universal method of forging the raw materials of planets and life, a process that may have dominated the early universe when similar starbursts were commonplace. Now we turn our attention to a phenomenon that allows us to literally see the invisible force shaping the galaxy. The intricate patterns of polarized light streaming from M82. To understand why this is so strange, picture a beam of light as a wave vibrating in all directions. Polarized light is light whose waves have been organized, made to vibrate predominantly in a single plane. In astronomy, this doesn't happen by accident. It's a powerful clue, a direct signature of the presence and structure of magnetic fields. And in the Cigar Galaxy, the story this polarized light tells is deeply confusing, revealing magnetic structures that defy our best models of how starburst galaxies should operate. The process itself is beautifully elegant. The galaxy's furious supernova have filled space with microscopic, needle-like dust grains. As these tiny particles are buffeted by turbulence and radiation, they naturally tend to align themselves with the local magnetic field lines, like countless compass needles all pointing the same way. When light from the galaxy's brilliant stars shines past these aligned grains, the dust scatters and polarizes that light. By meticulously mapping the direction and degree of this polarization across the entire galaxy, astronomers can essentially trace the invisible magnetic field lines, creating a detailed map of the forces at work. It's a technique that has worked well in common galaxies, producing predictable, large-scale patterns. But in M82, the resulting map is a chaotic and contradictory masterpiece. The prevailing theory suggested that the galaxy's powerful superwind would dominate everything. The logic was simple. Such a violent, focused outflow should drag the magnetic field lines with it, stretching them out perpendicular to the galactic disk in a relatively simple, organized, hourglass-like pattern. And indeed, when we look on a large scale, that's partly what we see. The field does appear to be stretched outward, following the direction of the wind. But when astronomers zoom in with modern, high-resolution telescopes, the picture fragments into something far more complex and bewildering. The polarization map reveals a stunning tapestry of small-scale structures, with field lines that are tangled, twisted, and often running completely contrary to the main outflow direction. This is the core of the mystery. The magnetic field seems to be caught in a titanic tug of war. On one hand, the immense force of the superwind is trying to pull it into a smooth, outflowing configuration. On the other hand, the sheer, relentless violence at the galaxy's heart is generating unbelievable turbulence. Each new supernova explosion sends a powerful shockwave rippling through the interstellar medium, churning the magnetic fields like a spoon stirring a cup of coffee, creating these localized knots and twists. The polarized light shows us a magnetic field that is both highly ordered and wildly disorganized at the same time, a state of controlled chaos that our simulations struggle to reproduce. Furthermore, the polarization reveals something strange about the dust grains themselves. The efficiency of the alignment process depends on the size and composition of the grains. The patterns we see in M82 suggest that the dust there is not only unusually abundant, but may also have a different make-up or size distribution than standard models predict. The extreme radiation and shock waves might be shattering larger grains into smaller, more easily aligned fragments, or perhaps coating them in exotic layers of ice that change how they interact with magnetic fields. The polarized light isn't just a map of magnetic forces, it's also a fingerprint of the dust's unique properties, another piece of the puzzle suggesting the galaxy's interior is a chemical and physical environment unlike any other. This contradiction forces a significant revision of our understanding. It shows that the magnetic fields in starburst galaxies are not passive passengers, simply blown by the wind. They are active, dynamic components of the system, storing vast amounts of energy and playing a crucial role in controlling the outflow itself. The field provides pressure that can help collimate the wind, and its tangled structure can regulate how energy and cosmic rays escape from the galactic core. The bizarre patterns of polarized light are therefore a direct window into the incredible energy balance at the heart of the Cigar Galaxy, revealing a level of magnetic complexity we are only beginning to appreciate. But our tour of the Cigar Galaxy's chaos isn't over yet, because some of its most peculiar signals aren't coming from vast, sweeping structures, but from tiny, brilliant points of light that blink on and off with a mind of their own. Scattered across the radio maps of M82 are enigmatic sources that refuse to stay still, changing their brightness dramatically over periods that can be as short as a few days or as long as several years. These aren't the steady glows of supernova remnants or the predictable pulses of pulsars. These are time-variable radio sources, and their flickering behavior points to a zoo of exotic, high-energy objects operating in the galaxy's extreme environment, phenomena that are exceptionally rare elsewhere in the universe. One of the most compelling explanations for these erratic beacons is the presence of microquasars. Imagine taking the incredible power of a quasar, a supermassive black hole actively devouring matter and shooting out jets at near light speed, and shrinking the entire system down to a stellar scale. That's essentially a microquasar. It's a binary star system where a stellar mass black hole or a neutron star is feeding on gas stripped from a companion star. As this material spirals inward, it forms a superheated accretion disk, and just like its gigantic cousins, this system can launch powerful, collimated jets of particles into space. In the radio part of the spectrum, it's these jets that produce a brilliant, variable light. The variability is the key signature. A microquasar doesn't feed at a constant rate. The flow of material from the companion star can be unstable, leading to periods of intense feasting followed by relative famine. When a large clump of gas suddenly plunges toward the black hole, it can trigger a massive outburst, brightening the jets and causing the entire system to flare up in radio waves. Then, just as quickly, it can fade away. The fact that we see multiple sources doing this independently throughout M82 suggests the galaxy is a fertile ground for these exotic binary systems, likely because the dense environment of the starburst core facilitates their formation. However, microquasars aren't the only potential culprits. Another fascinating possibility is that we are seeing flaring activity from intermediate mass black holes, those elusive cosmic middleweights we discussed earlier. If one of these objects is lurking in a dense cloud of gas, its feeding activity could be highly episodic. A sudden avalanche of gas onto its accretion disk could produce a tremendous flare of radiation across multiple wavelengths, including radio. The longer timescales of some variations lasting months or years could be more consistent with the larger, more massive accretion disks expected around these bigger black holes compared to their stellar mass counterparts. There's also the chance that some of this variability is driven by the unique environment itself. A supernova remnant expanding into an unusually dense or clumpy patch of interstellar gas would brighten as it plows into the material and then fade as it moves through it. Or a powerful shockwave from one supernova could suddenly compress a nearby cloud of magnetic fields and energetic particles, causing a temporary brightening in radio emission that then dissipates. In a region as crowded and violent as the core of M82, where shockwaves are constantly crossing paths, this kind of external triggering could be responsible for some of the flickering we detect. Each time one of these radio sources flares or dims, it sends a valuable message about the physical processes powering it. Astronomers carefully monitor these changes, creating light curves that act like a fingerprint for the type of object involved. A rapid, symmetrical flare that rises and falls quickly might point to a discrete event like a stellar eruption. A slower, more erratic brightening could indicate instabilities in an accretion disk. By combining these radio light curves with observations in X-ray and other wavelengths, scientists can start to piece together an identity for these mysterious objects. Their very presence and behavior add yet another layer of dynamic, evolving complexity to the galaxy, proving that even after decades of study, M82 is still capable of putting on a new and unpredictable show. Surrounding the brilliant, chaotic disk of the Cigar Galaxy, an even more immense and invisible structure looms, a vast, spherical halo of gas so hot it glows not in light but in X-rays. This is no ordinary cloud. It is a tenuous yet colossal atmosphere of million-degree plasma that envelops the entire galaxy, stretching hundreds of thousands of light-years into the intergalactic void, far beyond the limits of what we see in optical light. This extended X-ray halo is the final, breathtaking destination for the energy generated by the galaxy's internal frenzy, a permanent monument to its power that is slowly dissipating into the cosmos. The origin of this superheated gas is a direct consequence of the Starburst engine running at full throttle. Remember the phenomenal superwind, that hurricane of material blasting out from the core. That wind is not composed of a single type of material, it is a complex mix. The fastest component is the hot, ionized gas heated directly by supernova shocks, and it is this material that has the energy to completely escape the galaxy's gravitational grasp. As this supersonic wind erupts out of the galactic disk, it doesn't just vanish. It slams into the much cooler, more diffuse gas that already exists in the galaxy's outskirts and the space between galaxies. This collision is extraordinarily violent. The resulting shock waves act like a cosmic hammer, brutally compressing and heating this gas to temperatures reaching tens of millions of degrees. It is this process that inflates the giant bubble of hot plasma, slowly and continuously pumping energy into the halo. The sheer scale of this structure is what makes it so significant. This halo is not a small, localized feature. It is a defining characteristic of the entire galaxy, containing a significant fraction of the total energy produced by all the supernova that have ever exploded within it. To visualize its size, if the visible cigar-shaped galaxy were the size of a football, this X-ray halo would be the size of a large car parked beside it. It contains enough thermal energy to heat the surrounding intergalactic medium for millions of light-years in every direction, effectively preventing any nearby gas from cooling and collapsing to form new stars in satellite galaxies or future galactic generations. The Cigar Galaxy is not just a spectacle, it is a powerful engine of feedback regulating star formation across its entire local volume of the universe. Detecting this halo required a shift in our perspective, from optical telescopes to X-ray observatories like Chandra and XMM Newton. Because our atmosphere blocks X-rays, these must be space-based telescopes designed to see the universe in this high-energy light. What they revealed was a soft, diffuse glow enveloping M82, a glow that mapped perfectly to the predicted shape of the superwind's ultimate destination. By analyzing the specific wavelengths of this X-ray emission, astronomers could determine the exact temperature, density, and chemical composition of the gas. They found it was rich in heavy elements like oxygen, neon, and iron, the unmistakable fingerprints of material that had been forged in the hearts of massive stars and blasted out into space by their supernova deaths. We are literally seeing the galaxy polluting intergalactic space with the building blocks of future planets and life. This halo also presents a fascinating puzzle regarding its own stability and ultimate fate. The gas within it is so hot that it should be able to rapidly expand and simply dissipate into the near-perfect vacuum of intergalactic space. The fact that it maintains a coherent structure for so long suggests that something must be confining it. The leading theory points to the galaxy's own dark matter halo. While its distribution may be anomalous, its immense gravitational presence is still thought to form a deep potential well, an invisible bowl that helps to trap this hot gas, acting as a container for the galactic atmosphere. Alternatively, magnetic fields threading through the halo, though incredibly weak, might also provide enough pressure to help shape the plasma and slow its escape. This balance between the intense thermal pressure from within and the confining forces from without is a key area of ongoing study, teaching us how galaxies lose mass and energy over cosmic time. In the grand narrative of the Cigar Galaxy, this extended X-ray halo represents the final chapter in the story of its incredible energy output. It is the ultimate sink, the place where the fury of the starburst is finally converted into a more permanent, albeit fading, form. This hot gas will continue to expand and cool for billions of years. its enriched material eventually mixing with the primordial hydrogen of intergalactic space. In a very real sense, the violent death of stars within M82 is seeding the vast cosmic oceans with the heavy elements necessary for the formation of rocky planets and potentially life in the far distant future. The galaxy's influence, therefore, extends far beyond its visible borders, leaving a mark on the universe that will last long after its central fire has burned out. But just when we think we understand the violent ballet of matter in this galaxy, the individual dancers themselves start moving in ways that defy all choreography. If we zoom in from the grand scale of the superwind to focus on specific clouds of gas, their motions become deeply perplexing. These aren't the predictable, orderly orbits we see in common galaxies. This is a chaotic free-for-all where the basic rules of galactic motion seem to have been thrown out the window. Astronomers using high-resolution radio and millimeter-wave telescopes have mapped the velocities of these clouds, and the resulting data reveals a kinematic nightmare, a system in a state of profound gravitational disarray. The most fundamental rule broken is the simple direction of rotation. In a typical disk galaxy, the vast majority of gas and stars rotate in a single, coherent direction, tracing out the gravitational potential of the galaxy. But within M82, a significant population of gas clouds is caught moving in exact opposition to this primary rotation. They are streaming on retrograde orbits, essentially going the wrong way down a cosmic highway. The origin of these counter-rotating clouds is a subject of intense debate. Some could be the shredded remains of a small satellite galaxy that was cannibalized long ago and whose retrograde orbit is a lingering ghost of that ancient encounter. Others might be clouds of gas that were blown out vertically by the superwind, only to fall back into the disk at a bizarre angle, their momentum carrying them against the flow. Their very existence points to a galaxy whose history is far more violent and messy than its slender shape suggests. Even more bizarre are the clouds exhibiting extreme velocity dispersions. This is a technical term for a simple but shocking idea. Within a single, seemingly coherent cloud, different clumps of gas are moving at wildly different speeds relative to each other. Instead of a cloud moving as a unified block, it is shearing itself apart from the inside. This is the unmistakable signature of an environment dominated by powerful shock waves. As a supernova blast wave plows into a cloud, it doesn't hit it all at once. The shock compress ease the leading edge violently, accelerating it to a much higher speed while the trailing edge of the cloud is initially left behind. The result is a cloud that is being simultaneously compressed, stretched, and torn apart by its own internal motions. It's a state of such intense turbulence that these clouds are not stable nurseries for stars. They are temporary, chaotic structures being flash-heated and dissipated by the very forces that created them. The most extreme examples of this kinematic chaos are the clouds that appear to be completely unbound. Their measured velocities are so high that they exceed the galaxy's escape velocity, the speed needed to break free from its gravitational pull forever. These are not clouds that are falling back in or orbiting strangely. They are outright fugitives being ejected from the galaxy on a one-way trip into the emptiness of intergalactic space. This is the superwind operating at its most effective and most destructive. These clouds are the massive, dense clumps that were caught in the direct path of the erupting energy, blasted clear of the galaxy like leaves in a hurricane. Their discovery was a watershed moment, providing direct observational proof that starbursts don't just reshape galaxies. They can actively dismantle them by permanently removing their future star-forming fuel. This bizarre motion creates a serious challenge for astronomers. How do you even measure the mass of such a galaxy? The standard method relies on tracing orderly rotational motion to map out the gravitational field. But in M82, the motions are a tangled mess of rotation, outflow, inflow, and random turbulence. The velocity at any given point is a complex cocktail of forces, making it nearly impossible to disentangle the gravitational signature from the hydrodynamic chaos. The strange kinematics aren't just a curiosity, they actively obscure one of the most fundamental properties of the galaxy, hiding its true weight behind a veil of self-inflicted violence. This makes the Cigar Galaxy not only a laboratory for extreme physics, but also a cautionary tale for astronomers, reminding us that the serene rules of quiet galaxies do not apply where chaos is the natural order. Even the molecules within this chaotic galaxy tell a strange story, and one of the most telling chemical fingerprints involves a molecule we know well here on Earth: carbon monoxide. In the cold, dark clouds of interstellar space, carbon monoxide is far more than a simple gas. It's a crucial tracer, a tool astronomers use to map the invisible molecular hydrogen that forms the bulk of these star-forming nurseries. But when scientists pointed their most sensitive radio telescopes at the Cigar Galaxy, they discovered that its carbon monoxide was singing a different tune entirely. The ratio of its different isotopic forms is bizarrely skewed, presenting a clear chemical anomaly that points to a frantic and unusual history of star birth and death. To understand why this is so strange, we need to look at the isotopes themselves. Most carbon monoxide molecules are made with carbon-12 and oxygen-16, the most common and stable forms of these atoms. But sometimes a heavier isotope gets involved, like carbon-13 or oxygen-18. In a typical, calm galaxy like our Milky Way, the ratio of the standard carbon monoxide to these heavier versions follows a predictable pattern. It's a pattern set by the well-understood processes of stellar nucleosynthesis, how stars create elements, and the gradual mixing of these elements into the interstellar medium over billions of years. The Cigar Galaxy completely breaks this pattern. The amount of carbon-13 monoxide, for instance, is significantly higher relative to the common type than anyone expected. This anomaly is a direct clue that the galaxy's chemical evolution has been radically accelerated and altered by its extreme environment. The key lies in the sheer number of massive stars. These giant stars act as factories for carbon-13, producing it in their cores through the specific nuclear reactions involved in burning helium. In a normal galaxy, these elements are released slowly over time, gently enriching the surrounding gas. But in M82, these stars are living and dying at a breakneck pace, flooding the interstellar medium with a sudden, massive injection of this heavier carbon isotope. The galaxy's intense starburst isn't just creating stars, it's rapidly and efficiently polluting its own gas with the distinctive waste products of massive stellar evolution. Furthermore, the relentless churn of the superwind plays a critical role in mixing this cocktail. The powerful shockwaves from supernova don't just push gas around, they thoroughly stir it, ensuring that the newly forged carbon-13 from the latest generation of exploding stars is rapidly and evenly blended into the surrounding molecular clouds. This creates a galaxy-wide overabundance of the heavier isotope, effectively resetting the baseline for the entire interstellar medium. The carbon monoxide that forms in these clouds therefore naturally incorporates more carbon-13, creating the anomalous ratio we observe. It's a signature of a system that has experienced a sudden, violent, and recent phase of chemical enrichment, a stark contrast to the slow, steady brewing of a more sedate galaxy. This peculiar ratio might also be influenced by the very process of molecule formation itself. The extreme ultraviolet radiation flooding the starburst region is so intense that it can photodissociate, or break apart, standard carbon monoxide molecules in the outer layers of gas clouds. Some theories suggest that molecules made with heavier isotopes like carbon-13 might be slightly more resilient to this destructive radiation. If they are broken apart a little less efficiently, they could gradually accumulate relative to their lighter cousins over time. In the harsh, irradiated environment of M82, This selective destruction could be acting as a filter, further enhancing the anomalous ratio and adding another layer of complexity to the galaxy's unique chemical fingerprint. Ultimately, this isn't just a minor chemical curiosity. The ratio of carbon monoxide isotopes is a fundamental parameter that astronomers use to deduce the physical conditions within molecular clouds, such as their temperature and density. If the underlying ratio is completely different from the standard galactic value, then all those deductions could be systematically off. The anomalous ratio forces a recalibration of our tools for this specific galaxy, reminding us that the universe doesn't always follow the rules we establish in our own cosmic neighborhood. It is a powerful testament to the fact that a galaxy's most intense star-forming periods don't just shape its structure and dynamics, but leave an indelible and unique mark on its very chemical identity. And now we arrive at a mystery written in the language of heat, a puzzle that requires us to look at the Cigar Galaxy through a very specific and unusual lens. When astronomers point the powerful infrared eyes of telescopes like Spitzer and James Webb at M82, they capture more than just its immense glow. They break that light down into a detailed spectrum, a unique barcode of chemical fingerprints. Within this data, nestled in the mid-infrared range, are a set of spectral features that defy easy explanation. These aren't the broad, smooth hums of hot dust, but sharp, narrow emission lines and bumps that act like bright, neon signs pointing to the presence of very specific and unusual materials. These mysterious mid-infrared features are like finding unexpected ingredients in a familiar recipe, suggesting the galaxy's chaotic interior is cooking up compounds we rarely see elsewhere. The most prominent of these enigmatic signatures are known as the unidentified infrared bands, or UIBs for short. These are not new to science. We see them in many places in our own galaxy, often in regions where carbon-rich stars are shedding their outer layers. But in M82, they are overwhelmingly intense, shining with a brightness that is completely disproportionate to what we'd expect. These bands are widely believed to be the calling cards of large, complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs. Imagine these as tiny, flat flecks of soot, miniature networks of carbon and hydrogen atoms arranged in honeycomb patterns like microscopic pieces of graphene. They are common byproducts of combustion here on Earth, found in everything from car exhaust to charcoal grills. In space, they are thought to form in the outflows of dying carbon-rich stars. But their staggering abundance in M82 is the real head-scratcher. A starburst galaxy is supposed to be a hostile environment for these delicate molecules. The same fierce ultraviolet radiation that makes the galaxy shine also has enough energy to tear these complex carbon rings apart in a process called photodissociation. So why are there so many of them? One compelling theory is that the very violence of the galaxy is both the destroyer and the creator. The constant supernova explosions are producing a massive, continuous supply of carbon atoms, the raw building blocks. And while the UV radiation is breaking apart some PAH molecules, the dense, clumpy structure of the gas clouds might be providing safe havens. Deep within these dusty cocoons, the molecules could be forming or taking shelter, much like a person finding refuge from a storm in a deep cave. The intense shocks from the supernova themselves might also be forging new PAHs faster than the radiation can destroy them, leading to a bizarre, self-sustaining cycle of creation and destruction that results in a massive net surplus. Yet the plot thickens with the discovery of even more unusual features. Among the expected signals, astronomers have found strong, sharp emission lines that point to the presence of something far more exotic than sooty carbon, crystalline silicates. This is the scientific term for dust grains that have an ordered, structured atomic arrangement, like a perfectly arranged crystal lattice. Think of the difference between a beautiful, structured quartz crystal and a pile of shapeless, melted glass. In the calm, cold reaches of interstellar space, silicates are almost always amorphous. Their atoms are jumbled in a chaotic, disordered mess. Crystallization requires a specific and intense trigger, a sudden, powerful burst of heat that anneals the chaos into order, like a glassblower heating and carefully cooling sand to create fine crystal. Finding these crystals in such abundance within the superwind of M82 is a major clue to the transient, violent events happening there. They are the undeniable fingerprints of phenomenal thermal shocks. The leading hypothesis is that the expanding blast waves from individual supernova are passing through clouds rich in amorphous silicate dust. For a brief, searing moment, the leading edge of the shock front heats the dust grains to temperatures well over 1,000 degrees Kelvin, hot enough to literally melt them, and allow their atoms to reorganize into a crystalline structure before they rapidly cool again, locking that order in place. Each supernova shock acts like a cosmic kiln, firing the surrounding dust and transforming it from a common, amorphous state into a rarer, crystalline form. The presence of these grains tells us not just what is there, but what has happened to it, providing a detailed history of the thermal shocks that have rippled through the galaxy's gas. The combination of these two anomalous features, the overabundant organic pH molecules and the crystalline silicates, paints a picture of a chemical environment that is both incredibly rich and strangely contradictory. It is a place where delicate, carbon-based structures that are easily destroyed by radiation somehow thrive alongside mineral grains that have been forged in the heart of stellar infernos. This suggests a galaxy that is not just a single, homogeneous factory, but a complex mosaic of micro-environments. Dense, dark clouds might coexist right next to recently shocked, brilliantly hot gas, allowing for a wild diversity of chemical processes to occur simultaneously in close proximity. The mid-infrared spectrum becomes a chaotic chorus, with each unique feature singing the song of a different, extreme physical process, all overlapping into a single, magnificent and bewildering symphony of light. Amid the roar of supernovas and the blast of cosmic winds, the Cigar Galaxy communicates in more subtle languages as well, including the precise, amplified whisper of water masers. These are not your average water molecules, they are natural microwave lasers, and their behavior in Messier 82 is anything but predictable. Unlike the steady, reliable signals we might detect in common galaxies, the water masers here are prone to dramatic and baffling flare-ups, brightening intensely for short periods before fading back into the background noise, as if the galaxy itself is sending out erratic, high-energy SOS signals. To understand why this variability is so strange, picture how a maser works. It starts with a cloud of water vapor floating in deep space, often in the dense, hot region surrounding a newly formed massive star or a black hole's accretion disk. When this cloud gets pumped with energy, usually from intense radiation or a shock wave, the water molecules become excited. They then act like a cosmic amplifier, taking in passing microwave photons and emitting identical copies in a perfectly synchronized beam. In a stable environment, this produces a steady, detectable signal. But in the frantic core of M82, stability is non-existent. The energy pumping these masers is wildly variable, leading to outbursts that come and go in ways that defy simple explanation. These flares are likely tied to the most violent events in the galaxy. Imagine a titanic supernova exploding uncomfortably close to a maser cloud. The initial shockwave would violently compress the gas, dramatically increasing its density and pumping the water molecules with a massive, sudden burst of energy. This could cause the maser to flare with incredible brilliance, like a light bulb receiving a tremendous power surge. Alternatively, the flare could originate from the accretion disk around a black hole. If a large clump of gas suddenly spirals inward and plunges into the disk, the resulting release of gravitational energy could heat the surrounding water vapor almost instantly, triggering a brilliant but short-lived maser eruption. The real puzzle for astronomers is the timescale of these changes. Some masers flare and fade over a matter of weeks, while others vary over months or years. This rapid variability suggests the flares are being driven by events happening in extremely compact regions, perhaps no larger than our own solar system. Pinpointing the exact cause is like trying to diagnose an engine problem by only listening to the occasional backfire. Each flare is a vital clue, but the underlying engine remains hidden behind thick layers of dust and distance. This erratic behavior makes these water masers far more than just curiosities. They are invaluable probes. Each time a maser flares, it illuminates the conditions within its specific cloud, allowing scientists to measure precise temperatures, densities, and magnetic field strengths in these otherwise invisible regions. By meticulously monitoring their flickering light, astronomers can map the microenvironments around budding stellar giants and hidden black holes, gaining a unique window into the chaotic cradles of creation and destruction that power the Cigar Galaxy's relentless energy. Even the aftermath of stellar death in the Cigar Galaxy refuses to follow a predictable script. When astronomers map the locations of supernova remnants, the expanding, glowing shells of gas blasted outward by these titanic explosions, they don't find them evenly scattered across the starburst core. Instead, they appear in bizarre, clustered patterns, forming tight groups in some areas while leaving other seemingly identical regions completely empty. This strange distribution is a profound puzzle, challenging our most fundamental assumptions about where stars are born and where they choose to die. In a typical galaxy, you might expect a rough correlation between the locations of star-forming nebulae and the supernova remnants that eventually mark their demise. A stellar nursery gives birth to a generation of stars. Those massive stars live out their short lives, and they explode relatively close to where they were formed. But the core of M82 is anything but typical. The environment is so chaotic, so dynamic, that the connection between birth and death becomes tangled. The remnants are not neat tombstones marking a star's birthplace. They are chaotic signposts in a violently shifting landscape. One leading theory to explain these strange clusters involves the concept of triggered star formation. Imagine a particularly powerful supernova exploding in a dense region of the galaxy. The immense shock wave from that detonation doesn't just destroy, it can also create. As the blast wave plows through surrounding molecular clouds, it can compress the gas to incredible densities, actually triggering the collapse of new cloud cores and igniting a new wave of star formation. This creates a chain reaction. One supernova gives birth to a new cluster of massive stars, which then live fast, die young, and explode in relatively the same region a few million years later, creating a tight grouping of remnants. It's a stellar version of a family dynasty, with each explosion setting the stage for the next generation to be born and die in the same neighborhood. However, the empty zones are just as telling as the clusters. Vast stretches of the starburst region that are rich in gas and should, in theory, be filled with the remnants of dead stars are instead eerily silent. The explanation for these ghost towns may lie in the ferocious power of the superwind. In some areas, the combined effect of countless supernovae has blown a clean bubble through the interstellar medium. The superwind has essentially swept the region clear of both the dense gas needed to form new stars and the expanding remnants of the old ones, effectively evacuating the area and leaving behind a hollowed-out void. The remnants that do exist are therefore only found in regions where the gas is sufficiently dense to withstand the wind's erosive force, or in pockets that have been somehow shielded from the galaxy's relentless outflow. This uneven distribution also acts as a historical record, preserving the echo of the galaxy's violent encounter with M81. The gravitational tides that funneled gas into the core millions of years ago likely did so in a clumpy, uneven manner, creating an initial distribution of ultra-dense pockets within a more diffuse background. Star formation would have ignited first and most fiercely in these initial pockets, leading to the first waves of supernova. The remnants we see today might still be tracing the outline of those primordial density peaks, a fossilized imprint of the chaos that started it all. By studying the clustering, we aren't just looking at where stars died, we are reading a map of the galaxy's most intense initial trauma. Ultimately, this bizarre pattern forces a dramatic revision of how we model stellar life cycles in extreme environments. It reveals that in a starburst galaxy, the link between a star's birth and its death is not a simple local affair. The frantic pace of events and the overwhelming influence of collective feedback effects like the superwind mean that the entire core operates as a single, interconnected system. A supernova exploding in one location can dictate the fate of gas clouds light years away, preventing star formation in one region while triggering it in another. The distribution of supernova remnants is therefore the ultimate signature of this complex interplay, a snapshot of a system where creation and destruction are locked in a chaotic, galaxy-wide dance, leaving behind a graveyard arranged in a pattern we are only beginning to decode. Yet for all the violent motion and chaotic chemistry, perhaps the most subtly bizarre feature of the Cigar Galaxy is revealed not by what it emits, but by the specific color of its glow in the far infrared. When astronomers spread its infrared light into a detailed spectrum, they find its energy distribution is all wrong. It doesn't follow the smooth, predictable curve of a standard object heated to a single temperature. Instead, the graph shows a strange, lopsided shape with unexpected bumps and dips, a clear sign that the processes heating its immense clouds of dust are far more complex than anyone initially imagined. This anomalous far-infrared color is a quiet but profound clue that even our most fundamental assumptions about cosmic dust need rethinking in such an extreme environment. To grasp why this is so unusual, picture a simple piece of iron being heated in a blacksmith's forge. As it gets hotter, it glows first a dull red, then a brighter orange, and eventually a blinding yellow-white. A graph of its light output would show a smooth, continuous curve peaking at a specific color that corresponds directly to its temperature. Interstellar dust in most galaxies behaves in a similar way. It gets warmed by starlight and re-radiates that energy with a spectrum that peaks at a wavelength that tells us its temperature. In a calm galaxy, this creates a predictable relationship between the amount of light we see at different infrared colors. M82 completely shatters this simple relationship. Its far-infrared colors are far too red or cool in some bands and too blue or warm in others compared to what standard dust models predict. It's as if the forge is simultaneously producing metal that is both red-hot and white-hot, defying the basic laws of thermal emission. The leading hypothesis for this strange behavior points directly at the multiple, conflicting heating sources at work within the galaxy. This isn't a simple case of dust being warmed by a uniform bath of starlight. Instead, different populations of dust grains are being heated in radically different ways. One significant population is caught in the direct, blistering glare of the massive young stars within the superstar clusters. These grains are flash-heated to very high temperatures, and they emit most of their energy at shorter mid-infrared wavelengths, contributing to the warm component of the anomalous color. Meanwhile, another vast population of dust is located much farther from the immediate inferno. These grains are not heated by direct starlight, but are instead warmed more gently and uniformly by the intense, diffuse radiation field that fills the entire starburst region, or even by absorbing the light from the first, hotter population of grain. This dust radiates at longer, far-infrared wavelengths, creating the cool component, but the complexity doesn't stop there. The supernova shockwaves add another, even more violent heating mechanism. When a dust grain is suddenly overtaken by a million-mile-per-hour shock front, it isn't gently warmed, it is subjected to an instantane tremendous spike in temperature. A grain can be heated to sublimation temperatures in a microsecond and then cool back down just as rapidly as the shock passes. This transient, incredibly intense heating can make tiny grains momentarily behave as if they are much larger, hotter objects, emitting a brief flash of light that further skews the overall color of the galaxy. The anomalous far-infrared spectrum we see is therefore not the signature of a single temperature, but a messy, overlapping average of all these different heating processes happening simultaneously across the galaxy. Furthermore, the dust itself is likely the culprit. As we've seen, the dust in M82 is not the standard galactic blend. It is chemically anomalous, possibly enriched in certain types of resilient carbon grains and deficient in more fragile silicates. Different materials have different abilities to absorb and emit radiation. A carbon grain and a silicate grain of the same size sitting in the exact same radiation field will reach different equilibrium temperatures and will therefore glow with different colors. If the dust composition in M82 is truly unique, with an overabundance of one type of grain that efficiently radiates at far infrared wavelengths, it would naturally produce an overall color that looks excessively cool compared to a galaxy with a more normal dust mix. The strange colors are thus a direct reflection of the strange dust, a signature of the galaxy's unique and violent chemical history. This isn't just an academic curiosity. Accurately interpreting the far-infrared light from galaxies is one of the primary ways astronomers measure their total star formation rates, especially in dusty universes where visible light is obscured. If the color doesn't reliably indicate the temperature, and the temperature doesn't reliably indicate the heating source, then our standard conversions between infrared brightness and star formation power could be systematically wrong for the most extreme galaxies in the universe. M82, with its anomalous colors, acts as a crucial calibration point, forcing us to develop more sophisticated models that account for multiple heating sources and unusual dust properties. It reminds us that the universe is always more complex than our simplest models, and that true understanding requires listening to every subtle color in a galaxy's light. But perhaps the most elusive and tantalizing signal from the Cigar Galaxy is one that is almost impossible to detect. A whisper from a ghost particle that has traveled millions of years across the universe to reach us. In the deepest, most sensitive neutrino observatories on Earth, like the ice cube detector buried in the Antarctic ice, scientists have recorded the occasional arrival of tremendously high-energy neutrinos that seem to point directly back at Messier 82. This tentative connection, if confirmed, would elevate this chaotic galaxy into an entirely new category of cosmic object, one of the very few known extragalactic sources of these mysterious high-energy particles. Neutrinos are among the most bizarre and elusive fundamental particles in the universe. They are often called ghost particles because they have almost no mass, no electric charge, and they barely interact with anything at all. Trillions of them pass through your body every second from the sun and other sources, completely unnoticed. This same property that makes them so hard to detect also makes them incredible cosmic messengers. Because they hardly interact with matter, they can travel in perfectly straight lines for billions of light years without being deflected by magnetic fields or absorbed by interstellar gas. When a high-energy neutrino arrives at Earth, it points directly back to its source, offering a clear, unblemished line of sight to the most violent events in the cosmos. For a galaxy to produce detectable high-energy neutrinos, it must be hosting truly phenomenal particle acceleration processes. Neutrinos aren't produced directly. They are the secondary products of the most energetic particle interactions imaginable. The likely chain of events inside M82 begins with those protons being accelerated to near-light speed by supernova shockwaves. If one of these ultra-relativistic protons then collides with another proton or a photon in a dense gas cloud, the collision can create a shower of secondary particles, including short-lived pions. When these neutral pions decay, they produce gamma rays, but when charged pions decay, they produce muons and, crucially, neutrinos. Therefore, a detection of high-energy neutrinos is a direct signal that such violent proton collisions are happening, confirming that the galaxy is not just accelerating particles, but smashing them together with incredible force. The energy scale of these neutrinos is what truly underscores the power involved. The ones tentatively linked to M82 are not the low-energy neutrinos from the Sun. These are high-energy neutrinos, each carrying over 1 trillion electronvolts of energy. To put that in perspective, that's more energy than is achieved in the most powerful particle accelerators ever built by humans. For a single subatomic particle to carry that much energy means it must have been born in an environment of almost unimaginable violence, a natural particle collider operating on a scale we can scarcely comprehend. The Cigar Galaxy's supernova-driven shocks are one of the few environments thought capable of reaching such phenomenal energies. This potential link remains tentative because detecting neutrinos and pinpointing their origin is notoriously difficult. The Ice Cube Observatory detects neutrinos indirectly by waiting for the very rare occasion when a neutrino does actually collide with an atom in the clear Antarctic ice. This collision creates a muon that, moving faster than the speed of light in ice, produces a faint flash of blue Cherenkov radiation that the detector's thousands of optical sensors can see. By reconstructing the direction and energy of this flash, scientists can trace the neutrino's path back to a rough patch of sky. Several of these paths have led back to the general vicinity of M82, a correlation that is highly suggestive but not yet conclusive proof. If future data solidifies this connection, it would be a landmark discovery. It would not only crown the Cigar Galaxy as a cosmic particle accelerator of the highest order, but also provide a crucial missing piece in a multi-messenger puzzle. Astronomers have already detected high-energy gamma rays from M82, which are the telltale sign of proton collisions. High-energy neutrinos would be the smoking gun, the direct evidence that protons are indeed the particles being accelerated and collided. This 1-2 punch of gamma rays and neutrinos would irrefutably prove that the galaxy is a major source of the cosmic rays that permeate the universe, answering a question that has puzzled scientists for over a century. But to truly grasp the final, fundamental mystery of the Cigar Galaxy, we must perform what seems like the most basic measurement of all, weighing it. For any spiral galaxy, the primary tool for this is the rotation curve, a graph that plots how the orbital speed of stars and gas changes as you move outward from the core. According to the laws of gravity and the visible matter we see, we expect a very specific shape. Speed should rise steeply in the inner regions due to the concentrated mass there, then fall off just as steeply in the outer disks, like the trailing end of a bell curve. But for decades, we've known that in galaxy after galaxy, this doesn't happen. The rotation curve stays flat far out into the outskirts, a phenomenon that provides the strongest evidence for the existence of dark matter, an invisible halo of mass that provides the extra gravity to hold these rapidly spinning structures together. The Cigar Galaxy, however, takes this already puzzling reality and twists it into something even more baffling. Its rotation curve isn't just flat, it's anomalous, showing features and behaviors that simply don't align with any standard model, suggesting that the chaotic forces within it are warping the very rules of galactic motion. The first major anomaly is the sheer velocity and shape of the curve within the inner few thousand light-years. The orbital speeds climb with a breathtaking ferocity, reaching values that are incredibly high for a galaxy of its size. This indicates an immense concentration of mass in its central region, which aligns with what we see, the densely packed starburst core and its surrounding superstar clusters. But the curve doesn't just rise and then plateau neatly. It shows a complex, wobbly structure with bumps and dips, little kinks in the data that betray the presence of distinct, massive components pulling on the orbiting gas. These are the fingerprints of the galaxy's violent history. The gravitational pull of the central bar structure, forged during the tidal encounter with M81, leaves its mark. The collective gravitational influence of the superstar clusters themselves, each one a million solar mass beast, tugs at the surrounding material, creating localized accelerations and decelerations that are superimposed onto the overall rotation. It's not the smooth, clean curve of a simple, balanced system. It's the jagged, erratic signature of a place where mass is distributed in clumps and knots by relentless starburst activity. As we move further out, the plot truly thickens. In the outer regions of the galactic disk, the rotation curve begins to do something very strange. Instead of holding a steady flat line as the dark matter halo model would predict, it appears to decline. The orbital speeds of gas clouds at the galaxy's extreme outskirts seem to be dropping off, a sign that the gravitational grip of the galaxy is weakening faster than expected. This is the heart of the enigma. It suggests one of two radical possibilities. Either the dark matter halo surrounding M82 is far less massive or far less extensive than our cosmological models say it should be, or the simple assumption that these orbits are purely governed by gravity is completely wrong. This is where the galaxy's extreme nature makes a standard measurement nearly impossible. We assume that the motion of gas traces gravity alone, but in M82, the gas is not calmly orbiting, it's being violently blown about. The phenomenal superwind is not a subtle force. It is a hurricane of energy erupting from the core, and it imparts its own powerful push on the very same clouds of gas we use to measure rotation. So, the velocity we detect with our radio telescopes isn't a clean orbital speed. It's a contaminated signal, a messy combination of the gravitational pull from the galaxy's mass and the hydrodynamic shove from the superwind. A cloud that looks like it's moving slowly in its orbit might in fact be fighting a headwind, its true orbital speed masked by the opposing force of the outflow. Conversely, a cloud moving rapidly might be getting an extra kick from the wind at its back. This means the rotation curve we think we're measuring could be a profound illusion, a funhouse mirror reflection of the true gravitational field, distorted by the very cosmic hurricane we're trying to study. There's another, even more dramatic possibility. The dark matter halo itself might have been fundamentally altered. Some theoretical models suggest that the incredible, sustained energy output of the starburst could have done more than just push gas around. Through a complex gravitational interaction, the collective effect of all those supernova explosions might have actually transferred energy to the dark matter particles themselves. While dark matter doesn't interact with normal matter via electromagnetism, it does interact gravitationally. A sustained, powerful outflow could potentially have gravitationally heated the dark matter, causing it to expand outward and creating a darker, more diffuse, and less massive halo than a galaxy would normally form. In this scenario, the declining rotation curve wouldn't be an illusion. It would be the real signature of a galaxy that has, through its own unbelievable violence, punched above its weight and puffed away its own dark matter scaffolding. Untangling this, not deciding between a measurement corrupted by astrophysical weather or a halo permanently reshaped by stellar fury, is one of the greatest challenges in understanding M82. It requires building sophisticated computer models that simulate not just gravity, but hydrodynamics, radiation, and magnetic fields all at once. Astronomers must create a virtual twin of the galaxy and literally run experiments, turning the superwind on and off to see how it affects the perceived rotation curve. The answer holds implications far beyond this single galaxy. If the rotation curve anomaly is due to the superwind, then M82 serves as a massive caution sign, reminding us that in the most active galaxies, our standard tools for weighing the universe can be led astray by sheer violence. But if the dark matter halo has truly been modified, it would be a discovery of monumental importance, revealing an entirely new channel of interaction between the normal and dark components of the universe, a process we never dreamed was possible. The galaxy's final mystery, written in the subtle shifts of orbital speed, may ultimately force us to rewrite the rules of galactic evolution itself. From supergalactic winds that sculpt its iconic shape to the enigmatic whispers of high-energy neutrinos, the Cigar Galaxy has proven itself a universe of mysteries contained within a single, chaotic realm. We've journeyed through 30 of its most baffling phenomena, each one a testament to the raw, untamed forces that govern cosmic evolution. This isn't merely a collection of oddities, it's a deeply interconnected web of physics pushed to its absolute limit, where Starburst fuels cosmic hurricanes, magnetic fields channel unimaginable energies, and the very rules of chemistry are rewritten inside supernova-forged furnaces. M82 is more than a galaxy. It is a natural laboratory for extreme astrophysics, offering a front-row seat to processes so violent and so rare that they redefine our understanding of what is possible. What makes this galaxy so invaluable to science is the way it amplifies and intertwines these phenomena. The starburst drives the wind shapes the magnetic fields channel cosmic rays, and those cosmic rays might be producing the neutrinos that tickle detectors here on Earth. Every strange detail connects to another, painting a holistic picture of a system in constant, explosive dialogue with itself. We've seen how its anomalies force us to question the very tools we use to explore the cosmos, from the way we weigh galaxies with rotation curves to how we interpret the light from distant dust. It challenges not just what we know, but how we know it. The future of observing M82 is brimming with potential. Next-generation telescopes like the James Webb Space Telescope will peer even deeper into its dusty core, potentially resolving individual stars within its superstar clusters and uncovering the secrets of their bizarre formation. More sensitive neutrino observatories could finally confirm it as a definitive source of these ghost particles, solidifying its role as a cosmic accelerator. And as our simulations grow more sophisticated, we may finally untangle the greatest puzzle of all: whether this galaxy's missing dark matter is a phantom of our measurements or a shocking reality shaped by its own fury. This ongoing exploration reminds us that the universe's greatest wonders are often found in its most chaotic corners. The Cigar Galaxy is a perpetual mystery factory, and with every question we answer, a dozen new ones emerge from the cosmic smoke. Its story is still being written, and each new observation adds another line, so we turn the question over to you. Which of these 30 phenomena captured your imagination the most? Was it the UFO-like ultra-luminous X-ray sources, the frantic particle acceleration, or the ghostly gamma-ray flares? Share your thoughts in the comments below. Let's continue unraveling the secrets of this spectacular island universe together.